السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الرابعة إن شاء الله زينين. Function analysis first level, completeness of orthonormal system and Parseval's formula. Parseval's formula. We know complete orthonormal system, and now we take completeness of orthonormal system and Parseval's formula. The first definition: an orthonormal system sequence phi n belongs to natural number n in a Hilbert space in a Hilbert space H is equal to V inner product with completeness is complete if we call it complete if phi is equal to summation n from 1 to infinity phi inner product phi n times phi n for all phi belongs to H. This is definition. Remark: the above equality must be understood as the limit. The above equality must be understood as a limit. That means limit n goes to infinity norm phi minus summation n from, this is k here, k from equal 1 to infinity to n, another product phi k, and here phi k is equal to 0 for all phi belongs to H, where the norm is induced by the inner product. This is inner product. Now we take the example. Page number 1. Example: let phi n belongs to natural number n, be an orthonormal sequence in L2 of closed interval minus pi. Now if phi is equal to summation n from 1 to infinity phi n inner product phi n for all phi belongs to L2 of minus pi. This simply means that limit and goes to infinity integral from minus pi to pi absolute value phi of x minus summation k from 1 to n phi in product phi n here of x square dx equals 0 for all phi belongs to L2 of minus pi and this is star, where inner product phi n is equal to integral from minus pi to pi phi of x phi n of x conjugate dx. dx here. In general, star, this is a star, this is a star, limit integral from minus pi to pi, absolute value phi of x summation inner product phi n of x dx equals 0, where phi belongs to L2 of minus pi and closed interval minus pi. This is equality star does not imply pointwise convergence. i.e. phi of x is equal to summation n from 1 to infinity phi n, product here phi n of x for all phi x belongs to closed interval minus pi. Additional condition are required. We need additional condition to get this pointwise convergence. This equality doesn't imply now we take this is theorem. An orthonormal sequence. An orthonormal sequence in a Hilbert space H is complete if and only if, this is both sides, the condition inner product phi n is equal 0 for all n belongs to natural number n implies implies phi is equal to 0. This is in H. Now prove this theorem. You know this is theorem. An orthonormal sequence in a Hilbert space H is complete. We get the condition when this orthonormal sequence will be complete if and only if the condition, this is condition, implies if this is equal 0, so this is implies phi equals 0. If we get this is equal 0, then implies this implies phi equals 0, then the sequence is complete. This is theorem. We now prove this theorem. Let phi n, this is b sequence and belongs to natural number n, be an orthonormal sequence. This is orthonormal sequence in H. Then, from definition, phi is equal to summation n from 1 to infinity phi n, here phi n, for all phi belongs to H. This is from definition. Now this is first direction. This is complete. First, this is orthonormal. The orthonormal sequence is complete. In H, this is here is complete. Then from definition of completeness of orthonormal sequence, phi is equal to summation phi n for all phi in H. Now if phi n equals 0 for all n belongs to natural number n, then if this implies this, if we have this equality, and this is 0 for all n, so phi equal to n, then this implies phi is equal to summation n from 1 to infinity phi n, and this is equal 0, so this is equal 0 phi n, and this is equal 0 in H. So this is first direction. And the second direction, prove the second direction here, opposite direction. Here the second direction. Let us suppose that the condition phi n equals 0 for all n belongs to natural number n, implies phi is equal to 0 H. for all. Now let phi n belongs to natural number n, be an orthonormal sequence in H. Orthonormal sequence in H. Since H is a Hilbert space, this implies that summation n from 1 to infinity phi n, this is converges to some psi belongs to H, i.e. psi is equal to summation n from 1 to infinity phi n, and this is phi n. This is from theorem. This is from above previous theorem. We take it. This is Hilbert space. So this is Hilbert complete. So this there is a point in H such that this is summation equal to psi. This is page number 3. This is 2 and this is 3. Now if we show that psi is equal to phi, then we are done. Observe that inner product phi minus psi phi n. We take it. Try to get psi is equal to phi. Psi is equal to phi. So this we take this. This is inner product. And this is equal to phi n minus psi phi n, and this is equal to phi n minus, and this is psi. We suppose this is psi is equal to this summation. So substitute here this inner product summation I from 1 to infinity, inner product phi I, this and this phi n, and this is equal to phi n minus, move summation out, and this is actually real numbers or constant. Move here summation I from 1 to infinity phi I, and this is still phi n here. Then still phi n. and this is will be equal to phi n here, and this is will be summation I from 1 to infinity, and here inner product phi I, and here delta I n, because this is orthonormal sequence. So if I equal n, this is 1, and if I different from n, this is equal to 0. That means this is equal to phi n minus and this summation is equal to phi n. Phi n. Look here when phi, this is 1 when I equal n, so this is should be n equal 1, and if I different from n, this is equal 0, so this is will be equality phi n equal to phi n, and this is minus this equal to 0, the same. According to the initial assumption, we must have phi minus psi is equal to 0 in H, and this implies that phi is equal to psi. Assumption, because phi n is not 0, this is equal to this, and this is 0 quality, this is equal to 0 here, this we get this is equal 0, and this is phi n not 0, so must have this 0. If this 0 will be phi equal to psi. And now we get from this theorem, we know when the orthonormal sequence will be complete. If this condition here, page number 2, if this condition satisfy phi n equals 0 implies phi equal to 0, then the orthonormal sequence is complete. And this our condition here, phi n equal 0 implies phi equals 0. If phi n equals 0, this implies phi equals 0. Then we get this is will be 0. This is will be 0. Now Parseval formula. Theorem. This theorem. An orthonormal sequence phi n belongs to natural number n in a Hilbert space H is complete if and only if, this is also, again this is equality, if and only if phi square is equal, norm of phi square is equal to summation I from 1 to infinity absolute value inner product 5 phi I, this is equal to, this is square here, powers 2 for all phi belongs to H. If we get this equality, then the orthonormal sequence will be complete. And if the sequence, orthonormal sequence complete, then we get this equality. This is for both sides. Now this is page number 4, and we try to prove this theorem. Prove let, this is direction, let phi n belongs to natural number n be an orthonormal system. Sorry, orthonormal complete. This is complete sequence. Then if this sequence then phi is equal to summation I from 1 to infinity 5 phi I times phi I for all phi belongs to H. This is from definition of completeness of orthonormal sequence. This means limit n goes to infinity, norm phi minus summation I from 1 to n for inner product phi I norm is equal to 0. This implies limit n goes to infinity, norm of phi minus summation I from 1 to n, inner product phi I, this is phi I, this is square, equal to 0. Of course, here just the difference is here without square, and this is take square for both sides will be we get this. Now from Bessel inequality, from Bessel's equality, we get this norm phi minus summation I from 1 to n phi phi I square is equal to norm of phi square minus summation I from 1 to n inner product phi I, and this is square. This is from Bessel inequality. And this equals 0. That means this is equal 0, so that means this equals 0. So now we get, this implies phi square is equal to summation I from 1 to n. Let n goes to infinity. Let n goes to infinity, and this is will be to infinity phi I square for all phi belongs to H. So this is proof of the first direction. And the second direction, proof, let phi squared is equal to summation I from 1 to infinity absolute value inner product phi I square for all phi belongs to H. We have to show this is sequence is complete. Then zero is equal to limit n goes to infinity norm phi square minus summation I from 1 to n inner product absolute value inner product phi I square. This is, we apply here Bessel equality. Now this is by Bessel equality here will be equal to limit n goes to infinity. This is equality Bessel equality. By Bessel equality we get this is will be equal limit phi minus summation I from 1 to n phi I here phi I square. So this is equal to 0. This implies phi is equal to summation I from 1 to n phi I times phi I. This is equal to this. So phi n belongs to n is complete. This is page number 5. And I think this is enough for today. Thank you very much. Goodbye.